Welcome, everyone. I'm Wenxin Jiang, and this is my colleague, Jian. We are PhD students at the City University of Hong Kong. Our research focuses on developing statistical methods and software for large-scale genetic data analysis. But fortunately, we are here not talking about genetics or mathematics. Today, we are discussing how to safely push the speed limit of statistical models in Python. In field like genetics, speed is absolutely critical. The human genome has millions of variants. When we test their relationship to a disease, we execute billions of calculations. Without optimization, a single experiment can take months, so we must write fast code. But there's a strict rule. We cannot sacrifice statistical validity. If an optimized engine slightly changes the math, we are simply produce the wrong statistical conclusion faster. So today, we will explore how to prevent that. The governing rule of this framework is speed follows validation. Usually, we start with a baseline implementation that directly translates our mathematical formula into code. This code is often not optimized, but it serves as a reference. We then validate that this code produces the correct or expected result, often using simulations. Only after we have established that the baseline code is correct do we consider optimizing it for speed. Because the real-world data does not have the ground truth, if we simply run our code on it and we cannot check if the results are correct. Instead, we use simulation to create synthetic data sets where we know the underlying parameter and the relationships. By designing simulation scenarios, we can ensure that our implementation behaves correctly across a range of inputs. This allows us to test whether our accelerated code is producing the correct results compared to the non-ground truths and for our baseline implementations. This process of validating before timing ensures that we are optimizing code that is already correct, rather than optimizing code that may have bugs. Also, by using simulation, we can identify the bottleneck shapes in our code, which inform us on how to apply the appropriate optimization techniques. I believe most of you are familiar with software testing. In software engineering, we write various of tests to ensure that our code behaves as expected. This is exactly how we do with our statistical simulation. For example, the unit test in software engineering checked if a specific function produced the expected output of a given input. Also, in our statistics, despite of the randomness, we can set a fixed random set and check if our implementation produced the same result as our reference implementation. Software engineering also has the probability test, which check if certain properties hold under specific conditions. And in statistics, this could be checked if our method is irrelevant under null condition or if it is well calibrated. Also, the street test in software engineering checked how the system behaves under extreme conditions, which is analog to test our statistical methods with outliers or in high dimensions settings. The load test check how the system performs under heavy load, which corresponding to scaling up the sample size in our data. Finally, the regression test ensure the new changes do not break existing functionality, which is similar to ensuring our optimized code still pass the acceptance criteria we establish with our reference implementations. Python helps us a lot in this process. It allows us to write readable code that closely follows our mathematical formulas. It also has a rich ecosystem and libraries so that we can use to optimize specific bottlenecks without having rewrite our entire code base. Typically, we start with a NumPy implementation as our reference. We then run our validated checks to ensure that this implementation is correct. We perform the code to identify the hotspot, which are the part of the code that take the most time. These hotspots often have specific computational shape, such as numerical loops, dense linear algebra operation, or repeated work on shared arrays. Once we have identified the hotspot in our code, we can choose the appropriate optimization tool. For example, NumPy with plus, Numba, JAX, or multiple threading. We will demonstrate this using two workloads, k-means cluster and permutation test. Why we use these two examples? We choose k-means cluster and permutation test because they represent two common types of workload in statistical computing, each with different bottleneck shapes. K-means involve iteratively fitting, where we have a loop that assign point to the clusters and update the series centroid repeated until convergence. This creates a sequential state dependency. On the other hand, permutation has involved resampling inferences, where we start for data and compute statistics repeatedly. This process is often independent and can be high-dimensional, which present a different set of challenges for optimization. Now let's move on to the first workload. We use the famous arrays dataset to demonstrate the k-means algorithm. Each point in this scatter plot represents a flower. We want to cluster this point into three groups, which ideally corresponding to the three species of the arrays dataset. The purpose of k-means is to minimize the objective function value, also known as the inertia in k-means, which related to the sum of distance from each point to its assigned centroids. K-means involves several steps. First, we initialize the centroids, which can be done in various ways, but for this example, we will use a fixed initialization to ensure that our results are reproducible. Then we perform one round of algorithm, which consists of two steps. The assignment steps and the update steps. During the assignment step, we assign each data to the nearest centroids, and during the update steps, we recompute the centroids as the mean of the assigned points. We can see that the color of this point changes as the centroid moves. We will repeat these steps until convergence, which typically happens when the assignment no longer change. The key point here is that each update depends on the previous step of the centroids and assignment, creating a sequential dependency that can be a bottleneck in terms of performances. K-means is a useful test case for our framework because it exposes broad iterative pressure that are common in many statistical algorithms. The assignment update shape of k-means creates a bottleneck due to the repeated distance calculations, which have a computational complexity of n times k times d. Here, n is the number of samples, k is the number of clusters, and d is the dimensions of the data. We can validate our implementation by ensuring that we are using the same data, the same initialization, and the same stopping criteria, the same object functions. We can also test our implementation under harder scenarios, such as when there is overlap between the clusters, or when there is an imbalance in the cluster size, or when there is outliers, or when we are working on the high-dimensional spaces. By identifying the bottleneck shape in our code, such as loops, algebraic operations, or array manipulation, we can apply the appropriate optimization techniques. This iterative nature of k-means means that these pressures are repeated across iterations, making it a good example to demonstrate our framework for validating and optimizing statistical code. So before optimize our code, we must ask, did k-means really recover the true clusters? Therefore, we need to validate the method first. In our simulation, we use the ARI, which is adjusted random index, as a recovery score, where 1 is indicate the perfect recovery and the 0 indicate a random baseline. We test our implementation under various scenarios, such as the separation between cluster, which related to the overlap of the cluster, dimensionality of the data, presence of the outliers or the imbalance in cluster sizes. The key point is that we should not accelerate our code until we are satisfied with its performances. In the process of algorithm development, we usually detect what we call the failure mode, where the method does not perform well. And in this plot, we found there are several points that our method performed poorly. Although we can optimize our algorithm performances with our statistical tools, but to simplify in this presentation, we just give that step and assume it's ready for optimization. We will directly move to the validation check that we use to ensure our optimized codes produce the same result as our reference implementations. As previously mentioned, we use the same data, same initialization, same stopping criteria, and the same optimization function to validate our implementation. We already have a reference implementation in NumPy that serves as our executable oracle. When we implement our optimized version using Numba, JAX, or other tools, we need to ensure that it presents the result of the reference which is the same to the reference NumPy implementation. To compare this result, we look at both the objective function value and the predicted label. We set a tolerance level of differences in objective function, which is 1 times 10 to the minus 8 here. And in our test, we observe maximum differences of 3.1 times 10 to the minus 14, which is well below our tolerance threshold. Additionally, we check the label agreement measured by the ARI, and it is exactly equal to 1.0, indicating the perfect agreement between our accelerated implementation and the reference implementation. By passing these checks, we can confidently that optimized implementation are correct. Here are the details of the 3 implementation of assignment step of k-means. The first implementation used NumPy to express the distance calculations as dense matrix algebra. We compute the square distance using the formula that involved the sum of squares of the data point and the centroid. And then we use matrix manipulation to compute the cross term. This approach can be efficiently executed using BLAS libraries, which are optimized for performances on CPUs. And the second implementation used Numba to write loops that compute the distance and found the nearest centroid for each data point. The approach allowed us to parallelize the computations across CPU cores, which can be beneficial for smaller data sets or when the distance calculations are not easily expressed as a matrix operations. The third implementation used JAX to write a similar expression to the first NumPy one, but it is compiled to run on a GPU for potentially faster execution. JAX allowed us to write code that look like NumPy, but it can be execute on different hardware backends, including GPUs or TPUs. Each of these implementation has its own advantages and trade-off, depending on the specific bottleneck shapes. So which engine is the best choice? It depends on your bottleneck shape. In the first row, K and D are small. The work is scalar loop heavy. Many simple point-to-theoretic comparisons. Here, Numba is the natural fit because we can keep the algorithm close to the explicit loops, remove Python interpreter overhead, and avoid building a large dense distance matrix. And in the second row, the shape changes. With larger dimensions and more clusters, the distance computation becomes dense algebra. The BLAS libraries that back NumPy are highly optimized for this kind of work. That is why NumPy can beat Numba here. And in the third row, the work is large, regular, and batched for accelerator paths. JAX on GPU can help in this scenario, but only because there is enough device-friendly work to transfer data, batching, and pipeline overhead. It is not a free GPU win. So the conclusion is not Numba is fast or NumPy is fast or the GPU is best. The conclusion is validate the result first, and then we identify what is the bottleneck shape. Finally, we can choose suitable tools that fit that shape. Then we continue to the second workload. In the permutation test, we repeatedly start for the label of our data and compute group differences to build a non-distribution. This process involves 3 main steps. Here's our data. And we have 2 groups, A and B. We want to test if there are significant difference between this group A and group D for each feature. First, we start for the label and we are keeping the data matrix X unchanged. Second, we compute the group differences for each feature, which give us a statistic for every feature. Third, we repeat this process many times to build a null distribution. The repeats are independent, but they are not free in terms of computational cost. With R permutations and P features, the amount of our work scale as R times P, which can become a performance problem when there are many features P or many permutations R. The W mut X notation on this figure represent the larger implementation view, where we can batch the performances using matrix operation, but the underlying statistical question remains the same. The reference loop implementation of the permutation test iterates over each of the R permutations, computes the group differences statistic for each feature, and stored it in an R by P matrix. The approach is straightforward, but can be inefficient due to the large size of the resulting matrix. In contrast, the optimized path rewrites the computation to avoid explicitly from the R by P matrix. Instead, it processes the batch of permutation use a constrained matrix, W batch, that encode the staffer label, which is according to this line and that line. By multiplying W batch with the data matrix X, we can compute the statistics for a batch of permutation at once. This streaming approach allows us to handle larger workload more efficiently while still producing the same mathematical result. Before we can trust the optimized path, we need to verify that it produced the same result as the reference loop implementation. We run both implementation on the same input. which means using the same data matrix X and the same stream of stuff labeled. The reference implementation computes the statistics one by one in a loop, while the optimized parts compute them in batches using matrix operations. We compare the output of both implementations across several validation grade and random seed. The acceptance criteria, including the max absolute difference in p-value at the statistic, which are all below our setted tolerance threshold, so we can believe our optimized code. We also have checked the calibration of our permutation test under the null hypothesis. Here we generate data where there is no true effect, which we call the null condition, and run our permutation test to see how often it produces false positive. The type error rate here is the proportion of times we incorrectly reject the null hypothesis when it is actually true. We want this rate to be close to our nominal alpha level of 0.05. And in our calibration check, we estimate the type error and found it approximately 0.051, which we consider it to be well calibrated. Before we can optimize the performances, we need to understand how the runtime of our permutation test scale with the number of feature P and the number of permutation R. We run a local runtime scale experiment on my MacBook using a batch NumPy implementation with n equals to 500 samples. The result figures show that the runtime changes as we vary P and R. These local runtime signs help us to identify when the runtime starts to explode, which can inform our decision about when to move to more powerful hardware like servers or GPUs. By analyzing this scaling behavior, we can better understand the computational bottleneck in our implementation and make informed choices about optimization strategies. To determine when GPU can provide the speed up of our permutation test, we create a map that compares the end-to-end runtime of CPU and GPU implementation in a Linux server across different values of P and R. Here we found that the GPU can offer significant speed up when the workload is significantly large. For example, here when the R equal to 5,000 and P equal to 500,000, GPU can have a 8.5 times speed up. However, we also know that when the workload is large enough, the GPU will cause auto memory errors, and the CPU of our server still works, which can be considered a win of the CPU in this case. The decision map helps us to understand the condition under which GPU can be beneficial, and when we might need to rely on CPU resources instead. Parallelism also helps, but only up to a point. On the left, you can see the good news first. When we move from one worker to a few workers, total runtime drops a lot in both k-means and permutations. But the right panels tell the second half of the story. Each jump gives us a smaller marginal gain. The first jump is very valuable. Later jumps are much less valuable. And for the permutation workload, adding more workers at high ends can even make the things worse. So the lesson is not simply add more workers. The practical rule is use parallelism to capture the early speed up, then watch the marginal gain. When the curve flattened, more workers are no longer free. Before choosing Numba, NumPy, or JAX, we can also choose how the work is executed, processors, threads, or accelerator kernels. The workload here is permutation-style resampling. Many most independent Python tasks are running over data that we would like to keep shared in memory. with the standard GUIL build, adding thread pod executor workers does not give meaningful CPU parallelism. From 1 to 16 workers, the runtime is essentially flat, no improvement. With the free-threaded CPython build, the same thread-based design is scaled to about 4.7 times from 1 to 16 workers. That's the important evidence. The difference is not Python version. It is whether Python threads can execute the CPU-bound work in parallel. So to summarize, Numba conquers CPU loops, NumPy conquers dense algebra, and JAX provide GPU accelerations. Free-threaded Python resolve shared memory scaling limits. This brings us to the final decision guide. The flow work is systematic. We first simulate, then validate, then we identify the bottlenecks, and then we choose the suitable tool. On a personal note, I think choosing a computational engine is like choosing transportation. I travel here to LA from Hong Kong. For that distance, I took an airplane. Nobody expected me to swim across the Pacific, right? Then from LA to the Long Beach, I took the metro. And interestingly, Google Maps recommended me to take a 2.5-hour bus ride instead. That was a useful reminder. We still cannot rely on automation. And finally, from my hotel to this venue, I walked about 5 minutes. For that short local trip, walking had almost zero overhead. Calling a car wouldn't make it better. And the computational booklet works the same way. You look at the shape of the trip. If the booklet is the tight local numerical loop, many small point to centered comparisons, Numba may be the right tool. It keeps the algorithm explicit but removes Python loop overhead. If the booklet becomes dense metric algebra, NumPy is the express stream. Optimizing the linear algebra underneath. If the booklet is repeated CPU work over shared area, then multiple threads can help. And if the workload is mass, regular, and batch enough to amortize transfer overhead, this is when JAX or GPU become the right choice. So the route is not always use Numba or use NumPy or use GPU. The rule is validate first, understand the shape of the journey, then move to the booklet with the suitable tool and fit. Also, I believe everyone here has tried AI coding tools. They are impressively good at automating many of the mathematical tasks involved in coding and experimentation. Previously, there is a page for the effort for translating the original NumPy loops into a Numba version or JAX version. But with AI coding tools, such translation can be done without much manual effort. Even if you want to rewrite every code in Rust, AI can help you with that too. However, as a researcher, we need to take ownership of these scientific decisions and claims. AI can be a powerful assistant in implementing tasks, but it is ultimately up to us to ensure that our work is scientifically valid and that we are making accurate claims based on our findings. So to summarize the key message of this presentation, we make the statistic testable, then we found the booklet. By following this approach, we can ensure that our optimized code is both scientifically valid and efficient. Thank you for your attention. If you have any questions, please feel free to ask, and we will have a poster section during the Sunday. Here's the link and the QR code. You can scan it and find the slides of this presentation. Okay, thank you.